Here we're going to talk about the different tools that we have to describe electric interactions, like the electric potential energy, which has this mathematical form, the electric force, which has this mathematical form, the electric potential, which has this mathematical form, and the electric field as this mathematical form. Okay, and so what we're going to do is we've learned about all of these tools, and we've learned how to calculate them and apply them to different situations. But what we're going to focus on over here is the big square. So by the big square, I'm referring to this figure over here. And what that is a way of reminding ourselves and telling us what the connection or what the relation is between each of these tools. That is, how is, for example, electric field, how does it relate to electric potential, or how does electric potential relate to electric energy, or how do forces relate to electric fields, and how do we go translate between one or the other. Okay, so to talk about those relations, let's start off with a simple example. Okay, the example we're going to focus on is a system of two charges. Okay, so there's a charge which I'll call Q1 and another charge which I call Q2, and they are separated by a distance r, and this is labeled 1, 2. So r1, 2, the distance between these two charges. So we know that, for example, the electric energy is given simply as Kc Q1 Q2 by R1 2, where Q1 and Q2 are the magnitudes of the charges. Now, the force is also, we know, is the Coulomb force. So the force of experienced by particle 2 due to particle 1 is simply given as Kc Q1 Q2 by R12 squared, and then you have the vector over here R12 hat, right, the unit vector. And similarly, there is also a definition for the force experienced by 2 due to 1, which is simply given as, has the same form here in the numerator, except this is now R21 squared, which is the same thing in terms of distance. R21 and R12 in terms of distance are the same, but what's different really is the vector R21 hat, which actually points in the opposite direction. Okay. Similarly, one could calculate the potential, and the potential that charge 1 generates is given by Kc Q1 divided by R1. So what does R1 represent here? R1 simply represents some point in this coordinate space. It could be that one, or if you don't like that one, you could choose maybe this one here. It's any point, and in fact all points that you could consider in this space, and R1 is the distance from Q1 to that point in space. And similarly, R2 is the distance of that point from Q2, right? So the potential generated by Q1 is simply Kc Q1 by R1, and the potential generated by Q2 is Kc Q2 by R2, and the total potential generated at that point that we are considering is the sum of these two potentials. And you can repeat this exercise for all points on this plane. Similarly, you have the electric field, and the electric field is defined as Kc Q1. So the electric field generated by particle 1 is Kc Q1 by R1 squared times R1 hat. And what is R1 hat now? R1 hat is simply just the direction. If I'm standing on Q1 and looking at the point of interest, then R1 hat is the unit vector that points along this direction. Okay. And similarly, you have R2 hat for the electric field generated by Q2, and that is again, he's standing on Q2 and looking at the direction of this point, and that is R2 hat. And the total electric energy is given as the sum of these two. So let's start off with some simple connections. Okay, so we know that, for example, forces and electric energy are related through derivatives or integration, right, or slopes and areas. So let's actually just look at that. So for example, if we use some calculus, then the force, electric force, is simply given as the derivative dr. I put in this r hat over here. For those of you who are comfortable with a lot of math, you will know that this is not exactly true. This is true for a single charged particle, but it's not this equation. The vector nature of this equation is not quite true. There's more to it than there's more to it that I've omitted from here, just to keep this discussion simple. And similarly, you could go in the reverse direction. So suppose I knew the electric energy and I wanted to find the force, then I would take the derivative of the electric energy. But if I know the force and I wanted to find the electric energy, then I could do an integration. So this corresponds to some slope of a graph, and this corresponds to some area of a graph. Okay, and similarly for the same is true for electric fields and potential. So potential and electric field is given either by derivatives or through integrations. Let's verify these relations. So for example, for the simple two-particle system, I have the electric energy being given by as Kc Q1 Q2 over R, and I'm not writing the label 1 2 over here because I want to keep things notation simple. So then derivative of du dr is well, Kc is a constant, Q1 is a constant, Q2 is a constant, and so I just need to differentiate R, and so the differentiation of that is Kc minus Kc Q1 Q2 by R squared. Okay, and so if I put all of this back in this formula up here, I end up with the force equation. So that was verified that way. And you can try the same for electric fields and potential as well. So you will see that for the electric field for particle 1 is given by taking the derivative of the potential for particle 1, and same for particle 2 and particle so for particle 2. Now let me so we can put over here that if I wanted to go from force to energy, then I would apply this relation. I would apply this relation up here, right? So that's how I would go from force to energy. And if I wanted to go from energy to force, then I would use this relation instead. And the same thing for electric fields and potentials, right? So that's how I would go from electric fields to potentials. So what's left now is for us to figure out how do we go between forces and electric fields and potential and potential energy. And so if I stare at these equations for a bit, then it looks like the only thing I really need to do is, if I want to go from, say, for example, electric field to force, then all I really need to do is multiply the electric field with the charge Q2, or maybe I could multiply the this second electric field with the charge Q2. So very naively, we can just write down that the relation between this is that the force and electric field are related simply by the force vector being given by charge multiplied by the electric field, and the potential energy being multiplied. Potential energy is given by charge multiplied by the potential. So that completes our square of relations. However, there is one subtle point that I want to emphasize on, and that is to do with these relations between potential energy and potential. The question that we always need to ask ourselves is which charge are we referring to over here? Are we referring to, in this particular example, are we referring to Q1? Is Q Q1 or is Q Q2? Right. Similarly for the potential and potential energy, does Q correspond to Q1 or does it correspond to Q2? Right. And so that is the subtlety that we're going to try and understand next, and try and understand what exactly goes into how do we really translate from these either side. Okay, so for that let's look at this system again, Q1 Q2. Okay, and let me consider a point over here. Okay, Q3. Okay, and I'm going to use the example of sorry, I'm not considering a point, I'm just considering a point over here, and let me use the example of potential. So if I want to know what the potential is at this particular point, then I need to know what the distance r1 from this point is, the distance r2 from this point, and then the total potential is given by the sum of each potential, so v1 which plus v2, right? But v1 is simply kc q1 by r1 and v2 is kc q2 by r2. Okay, so I have this two particle system and I know the potential. Now let me ask the question that, all right, if I wanted to know how these two charges, so let me write this question out explicitly. If I want to know how these two charges affect a third charge that is placed at this point, and let me call this point P, is placed at P, then I, for the time being, I don't know what that charge is, so I'm going to give that a different label. So I'm going to classify this in the following way. This Q1 and Q2 are source charges. Okay, and I'm going to introduce a new charge called Q3, which I will refer to as the test charge. Okay, because I want to test what is going to happen to this charge when some charge when I place it at the point P. So if I wanted to do that, then I could, for example, calculate the potential energy, and if I go back to this relation that we've written up here, right, then I would say that the potential energy is given by Q3 times V, which is, if I substitute all of this back in, that becomes Kc Q1 by R1 plus Kc Q2 by R2, and if I expand the brackets, that becomes Kc Q1 Q3 by R1 plus Kc Q3 Q2 by R2. Okay, so this then corresponds to the potential energy. But you have to ask yourself this question. This is potential energy for which system? Okay, so let's look at a system schema. So if I have Q1, Q2, and Q3, and they all interact with each other, where would I draw the system boundary? Okay, that is, should I draw it around Q1 only, or should I draw it only around Q3? Should I draw it only around Q2, or should I maybe draw it all around them? So let's actually write down what um, uh, the so let me imagine if I want to write down the let me get rid of all of this. um, let me actually write down the potential energy if this corresponds to the system boundary, right? So the total energy. So the total energy of the system is actually given by the sum of all possible combinations. So that's Kc Q1 Q2 by R12, right? Plus Kc Q1 Q Q3 by R13, right? And Kc Q2 Q3 by R23. So all possible combinations. There's 1 2, 1 interaction with 2, 2's interaction with 3, and 1's interaction with 3. So there are these 3 possible combinations that I need to write down, and that gives me the total energy. Now let's compare this with our what we've written down up here. So these are not the same. So this represents actually the total energy for this. But what does this expression represent actually? Remember, we derived this expression by saying that, oh, this must be Q3 times the potential. So what energy does this represent? So that's actually the slightly tricky point or subtle point that we're trying to understand. So this does not represent the total energy of this system. I mean, this does not correspond to this. It in fact doesn't even correspond to this case where I'm only circling Q1, right? And in fact, this is where the system schema representation kind of breaks down, because what this represents actually is the let me write that down. So this expression up here, so this represents the interaction energy of interaction energy between particle 1 and 2 and 3, sorry, and particle 2 and 3. Okay, so this is the interaction energy. How much energy of interaction does particle 2 have when it's interacting with particle 1 and 3? 1 and 2. What it doesn't include and what's missing is um, the term over here, Q1, Q2, right? Because we're not concerned about how Q1, what effect Q1 has on Q2. We are only interested in some other particle being over here, then and asking the question, what effect would this have on some test charge placed at that point, right? So this is a very subtle point, and when you has to keep in mind these things when converting between um, electric potential energy and the potential itself. That is, what is Q here? Q really corresponds to the test charge, and the potential is generated by all the source charges. What is the test charge and what is the source charges? But that is really decided by you or the system you're considering. For us, the case that we're considering is, oh, I know what Q1 and Q2 is, and so they form my system of source charges, and I want to figure out what would happen to a test charge Q3 that is over here.